All right, today we're going to tackle a classic physics problem. It's one of those that seems totally impossible at first, but when you use the right tool, it reveals a shockingly simple answer. So let's dive right in. So, right off the bat, here's the big question. If you have an infinite plane, that means you have an infinite number of charges. How on earth are you supposed to add up the electric fields from all of them? I mean, it sounds impossible, right? Like a calculation that would literally take forever.
Okay, so this is what we're looking at. Just picture a perfectly flat sheet that's infinitely large, with positive charge smeared out perfectly evenly all over it. We've got a name for that even spread, surface charge density, and we call it sigma. Our mission, should we choose to accept it, is to find the electric field E that this massive charged sheet creates.
Now, you could try to solve this the hard way, by adding up the little bit of electric field from every single point charge on that plane. That method's called direct integration, and trust me, it's an absolute nightmare. The math just explodes in complexity. But yeah, we're not doing that. Nope. Instead, we're going to pull out a secret weapon from our physics arsenal, and that is Gauss's law. This thing is just an incredibly powerful shortcut. It lets us sidestep all that messy math and solve problems like this one with a kind of elegance. So, what exactly is Gauss's law? Well, putting it simply, it says that if you draw any kind of imaginary closed surface, think like a bubble or a box, whatever you want, the total amount of electric field poking out of that surface is tied directly to the total charge you've trapped inside it. It's this amazing fundamental link between what the field is doing on a surface and what charge is hiding inside it. But here's the thing about Gauss's law. The real trick isn't just knowing the formula. It's about being clever. We have to pick the perfect imaginary surface. We call it a Gaussian surface. One that perfectly matches the symmetry of the problem we're trying to solve. That is where the magic really happens.
Okay, so let's really think about this symmetry for a second. We have a plane that stretches out forever in all directions, and the charge on it is perfectly uniformly spread out.
I mean, seriously, think about it. If you're a tiny observer floating above this infinite plane, and you move left or right or forward or back, does anything change? No. It looks exactly the same in every direction. It's infinite. And that simple fact has a massive consequence. The electric field strength just can't change as you move parallel to the plane. So, if the world looks the same in every sideways direction, then the electric field can't play favorites. It can't point left or right. It has to point straight away from the plane, totally perpendicular. And that means the only thing that could possibly affect the field's strength is how far you are away from the plane, that up and down distance we're calling z. Okay, so knowing the field only points up and down, what shape should we choose for our Gaussian surface? What's the perfect trap to take advantage of that? You got it, a cylinder. A simple can shape, positioned so it pokes right through the middle of the plane, is absolutely the ideal choice. And why is it so perfect? Well, think about it. The flat top and bottom caps, the electric field pokes straight through them. Perfect. And the curved sidewall, the electric field just skims right past it, totally parallel. This setup is going to make our math just ridiculously clean. Okay, so we've got our strategy, we've got our perfect Gaussian surface. Now it's time to actually apply Gauss's law and see what happens. And you're about to see just how incredibly simple this whole thing becomes. So remember, Gauss's law cares about the total electric flux going through our whole closed surface. For our cylinder, we can break that down into 3 easy parts: the flux through the flat top, the flux through the flat bottom, and the flux through that curved side. And right away, we get a huge win. The flux through that whole curved side, it's 0. A big fat 0. Gone. But why? Well, remember, flux is all about how much the E field pokes through a surface. Since our field lines are all pointing straight up or straight down, and the sidewall is, well, it's vertical, the field lines just kind of skim along the surface. They never actually pierce it. Or, if you want to get mathematical about it, the E field vector and the little area vector ds are at a 90-degree angle to each other everywhere on that side, so their dot product is always 0. So that simplifies things a lot. The total flux is now just the flux through the top cap plus the flux through the bottom cap. On the top, the field E goes through area S, so that's E times S. On the bottom, same thing, E times S. Add them together and we get 2 times E times S. That's the left side of Gauss's law. And the right side, the enclosed charge,
That's even easier. It's just that charge density, sigma, multiplied by the area of the little cookie cutter circle our cylinder punched through the plane. So sigma times s.
Okay, so now we just set the two sides of the equation equal to each other. The flux part equals the charge part. We have everything we need to solve for E. And the answer that pops out is, well, it's shockingly simple. And boom, there it is. We just do a little algebra, divide both sides by 2s, and look at that. The s, the area of our made-up cylinder, it just cancels out from both sides. It doesn't even matter. What we're left with is that the electric field, E, is just sigma divided by 2 epsilon naught. That's it. It's beautiful. Okay, wait. Let's pause for a second and really look at this result. I mean, really look at this equation. Do you see a z in there, a variable for distance? Nope, it's completely gone. And that is the mind-blowing, totally counterintuitive result here. The strength of the electric field from an infinite plane of charge doesn't depend on distance. It's constant. It doesn't matter if you're right up against it or a million miles away, the field has the exact same strength. How wild is that? And this graph just shows it perfectly. You can see on one side, for any positive z, the field is just some constant value. And on the other side, for negative z, it's the same constant value, just pointing the other way. The key thing is, the magnitude, the strength of that field, is the same everywhere you go.
So, what we've just seen is the absolute power of symmetry. We took a problem that looked infinitely hard, and just by being clever and using the right tool, Gauss's law, we made it, well, not so hard at all. And the result we got is this bizarre, perfect, uniform electric field. Now, this isn't just some abstract textbook problem, by the way. This idea is the fundamental principle behind capacitors, you know, the little components that are in pretty much every electronic device you own. But okay, what we used here was the integral form of Gauss's law, which leads to a pretty interesting question. What about the local form?
It's a whole other way of looking at things, really. So if you'd like to see an explainer on that topic next, definitely let us know in the comments. Thanks so much for diving into this with us. We'll see you in the next one.